Given how advanced fighter jet aerodynamics are, you think you can't really improve upon them very much. Well, one area that could be improved upon is the region that produces vortices. So in figure 1 here, we see a basic fighter jet, and the important thing to note is that most fighter jets produce vortices over the front of their wings, like here. These vortices then travel down over the top of the wing, and believe it or not, but these vortices are created on purpose and for the reason of allowing the jet to produce more lift at higher angles of attack. And the general mechanism it produces is these vortices are very low pressure cores. As they flow over the wing, you now have low pressure there, and as such, flow over the top of these vortices and now pulled down onto the wing. As a result, you can fly at far higher angles of attack, and the flow will still stay attached. And the technical term for this type of lift is vortex lift. And actually, if you don't know much about it, then check out a video on our YouTube channel called Aero Fundamentals number 43, Delta Wings Explained. In that video, we go through this exact flow physics, and most modern fighter jets use this. So in figure 2, we see the idea of this vortex lift, and in particular, the graph that shows the lift coefficient with the angle of attack. So this left part here. So let's quickly explain what this is. The graph is divided into two parts, the potential lift part and the vortex lift part. The potential lift part is pretty much the lift from wings in general, but the vortex lift is the bit that you get from the vortices here. And there are a few things to note. The first is that from the graph, you might think that you get more lift on an airfoil that also produces vortex lift than an airfoil that doesn't, because you have the potential lift plus the vortex lift on top of it. But that's not actually true. And in fact, if you look at the y-axis, you see that the lift coefficient only hits about 1.2 at an angle of attack of about 30 degrees. Now, not every single wing with vortex lift will produce this exact amount at this angle of attack, but it's an approximation. And the important thing to note is that if you're only hitting 1.2 at a very high angle of attack, like 30 degrees, then that's not very great. I mean, most wings will hit 1.2 at like 12 degrees or so. So for this wing with the vortex lift, you have to go to like 2.5 times the angle of attack to get the same kind of lift coefficient still. So when you have vortex lift over an airfoil, you get less lift at pre-stall angles of attack. But that is only half the story, because as we can see in this graph, the wing here is producing good lift at really high angles of attack. So at 30 degrees, for example, almost every wing will be stalling by now, but this one isn't. So that is the trade-off you get, where you have vortex lift where you may not get good lift at low angles of attack, but you get really good lift at high angles of attack. And that allows you to fly at very steep angles and still maintain control. So what vortex lift really does is flatten this lift curve slope and then just extend it across in the angle of attack. And in fact, 30 degrees isn't really that high for vortex lift. Some wings can go to like 60 degrees before hitting stall. And just as a quick note, one of the early researchers into this was a guy called Paul Harmos. And if you want to learn more from the very beginning about vortex lift, then check out some of his papers, because they're really interesting. Now, there are a bunch of ways you can create these vortices and the subsequent vortex lift. But the two most common in practice today is through something called a delta wing and something called a leading edge extension. In effect, they are pretty much the same thing when you use pretty much highly swept leading edges. So you can see here on this planform here, this triangle planform, and you need to make sure that the leading edge is sharp too. Then what happens is that the flow rolls up over it, as shown in figure 2 here, as the flow goes up around, and this figure here. And then vortices are created and they extend down to the wing. With the delta wing, which is this triangular planform here, you have the entire wing with these leading edges, but then you can also have leading edge extensions, which we see in figure 7, and they create pretty much the same kind of idea. And the idea of these things is, if I zoom in a bit, right here, these two parts here, like these little bits coming out from the actual wing and like strapping onto the fuselage, and it's even more sharply swept than the rest of the wing. So the regular wing is kind of like a delta wing, but then you have these leading edge extensions, which then extend the wing platform. And this is really the far more modern way of producing vortex lift, because if you look at all the airplanes that produce vortex lift these days, this is a lot more common. And note that this is still coupled with a delta wing platform, but this is also a delta wing because of transonics and supersonics to suppress drag. I don't want to get too much into it because it's very complex, but one major reason why wings still use delta wing platforms with these leading edge extensions is that this highly swept leading edge doesn't hit the shock that is forming from the rest of the aircraft upstream. Anyway, the leading edge extensions are called LEXs for short, LEX, and there is also another minor variant called leading edge root extension, or LERCs for short, with an R in there. This is literally just when the extension starts from the root of the wing, which is pretty much always anyway these days. And these LEXs are super effective because they create these vortices that travel over the wing and allow fighters to go very steep angles of attack, but they're not perfect, and there's still room for improvement, and that is where this paper comes into it. And back to figure 1b, up here, there's figure 2, and figure 1b should be here. These ones here, this apex flap idea. This is where the front is this LEX still, but it's on a hinge, and you can now tilt it up or down depending on the angle that you want. And this idea is called LEVCON, which stands for Leading Edge Vortex Controller. And this can hopefully allow the jet to go even higher angle attack, because you can now pivot these extensions to still get the vortex lift. At least that's the idea. And the reason why this is good is because, or at least in theory, is because with regular LEXs, once you hit a certain angle attack, the vortices coming off them burst, and then you lose that vortex lift. With these apex flap LEVCON idea things, hopefully you can still produce these vortices at higher angles of attack. And another hope is that because you can move these LEVCONs, you can trim the aircraft so that you can achieve the optimal lift-to-drag ratio depending on the flight conditions. Now, to test if these LEVCONs work, this paper, which is called Leading Edge Vortex Controller, LEVCON, Influence on the Aerodynamic Characteristics of a Modern Fighter Jet, and the DOI is down here. So in this paper, they used OpenFOAM, which is a very powerful CFD software. And if you want to learn how to use OpenFOAM yourself, then you might be interested in our courses that you can find in the link below on our website. And they used RANs here, which is fine for pre-stall angles of attack. Past stall or even during stall, RANs is quite difficult to get right because of the unsteadiness associated with the aerodynamics there. They then used the KME SSD turbulence model, which is great. That means you can have a very large range of Y plus values in your mesh and still be okay. We'll get into that a bit more later. And the reason why that's important is because fighter jets are really big machines. They don't look that big. Once you go up close to them, you realize just how big they are. And to get a Y plus value around 1, which is often wanted, you need to have a huge number of cells, far more than you need for a car because a car is much smaller. So by going to something like the KME SST model, you can go up to a Y plus value of maybe 300, depending on who you ask. It's like between 150 and 300, 400. And the authors took advantage of this flexibility because they had Y plus values around 50. And we'll get into their mesh a little later on. Let's first look at their geometry because that's the thing that everything else is built around. So in figures 6 and 7, if we scroll down a fair bit, just down here. Okay, so figures 6 and 7, let's zoom out a little bit. So their plane that they designed pretty much from scratch is a 5th generation style fighter, where first of all, you have a very stealthy planform. Then the wing and the tail planforms are what you would expect with these like delta wing, LEX, and plus these tail flaps that can move around. And it's also a twin engine, which is very common for 5th gen fighters. Now in figure 6, we see the airfoil cross section, if we zoom in a little bit. And you can see 2 here. So something to note is that they are both NACA style. Now in 5th generation fighters, they don't strictly use NACA airfoils. I mean, in the US, other countries have different airfoils, but even in the US fighters, the airfoils are based on NACA profiles, but they are modified to delay shocks or increase maneuverability in certain situations or increase control, etc. The NACA profile is really just like the general guideline. Anyway, in table 6, we see the numbers of the airfoils. So both have a maximum thickness of about 6%, which occurs at 40% and 50% of the chord respectively, of the chord, sorry. One is completely symmetrical, while the other is only slightly cambered, 1.1% that occurs at 50% of the chord from the leading edge, so halfway down. And the NACA 64206 was used for the wings, and the NACA 16006 was used for the tail. So it makes sense why the tail airfoils aren't cambered, because if they were, then you would naturally produce a nose down pitching moment, even at 0 degree angle attack. So having them uncambered helps keep the airplane stable at low angles of attack, and hence it is a little more efficient as well during cruise. Now in table 5, We see some details of their LERCs description, which is they're swept at 64 degrees. So that's very aggressive. That means that this angle here coming down to begin with, that's 64 degrees. Then the rest of the wing is, what was it here? It came in at 42 degrees. So to give you an idea of how different that is to many modern passenger airliners, their wings are often swept at like 22.5 degrees, 25, 27.5 degrees. Those are pretty common numbers. So these are far more aggressive. And there's actually something called anhedral to the wings as well, which if we look at figure 7a, so this front one here, if we zoom in, so these wings have something called anhedral. And if you look at these wings, you can see that they are kind of drooping down a little bit. This is anhedral. If the wings were flexed up, that would be dihedral. The major benefit of anhedral is that it makes the planes more agile, while dihedral makes them more stable. There are some other benefits too, depending on the type of airplane you have. But for fighter jets, this is one of the major benefits of anhedral. It makes it far more agile. So let's now get into the CFD setup because it's quite complex. So we've already covered that it is RANs, and to first validate their general CFD approach, they did just a regular 2D NACA 0012 airfoil, which is probably the most common airfoil out there. It's used almost everywhere. That's a bit too far down. Let's go higher up. That's where they have their 2D CFD. So they show their mesh in figure 4 here. And this is just a simple case of their 2D airfoil to get their feet wet with the CFD and to see if their general approach is good or not. And it might look like a funny setup. For example, in figure 4a, we see that the inlet is this really circular shape. It goes more than 180 degrees. It's like maybe 210 or so. And then the airfoil is placed right in the middle here, smack bang. Then the rest of the domain is this rectangular shape. So the top and bottom and the outlet. So the reason for this curved inlet is so that you can change the angle of attack without remeshing. All you need to do is change the inlet flow angle, and because the inlet is circular to begin with, you don't have to worry about the separation at the edges that would usually occur if you had a rectangular domain in general. So one thing that I would like to see here is actually more that the trailing edge section fans out a bit more. So let's zoom into figure 4D to explain what I mean here. So in figure 4D, we see the mesh around the trailing edge section of the wing, of this NACA 0021. Or 0012, sorry. And you can see this really dark line extending to the right away from the trailing edge of the airfoil towards the outlet. So that dark line is literally all these tiny cells that it just looks like this dark line because you can't really see them because they're so tiny. But notice how thin it is. That is fine for variable angle of attack because the wake from the airfoil will be highly resolved and is very small too. But if you go to high angle of attack, the wake from the airfoil will now completely miss this dark region. It will go down more at an angle, and these really fine cells will sort of capture more like regular flow, not really much of a wake. So by fanning out this line, you should have a really fine cells above and below it too. So when you go to high angle attack, you can get more accurate results because you resolve the wake more. As it stands, with this type of mesh here, there is a decent chance that at high angle attack, you won't get as accurate a wake resolution as if you were to have this dark region fanning out more and taking up more of that wake. So in table 1, we see some of the flow characteristics, and first of all, it is compressible. Once we get to table 1 here. Sorry, I mean to say that it's incompressible. And that's fine here because the Mach number is 0.15. And actually, if you want to learn more about how the Mach number affects the density and compressibility of air, and then when to use compressible versus incompressible, then check out a video on our YouTube channel called When is Air Compressible? Air Fundamentals number 48. In that, we go through the equations describing the density of air with the Mach number. Now, the Reynolds number is 6 million here, and which at this number, you could kind of use a bunch of different turbulence models and still get pretty accurate results. I mean, sure, the K-Mig SST is great, but you could also go to like the Spallet-Almaras and still get good results. And the major benefit of that is that if you were to use a Spallet-Almaras, it would be a little quicker because that only uses one equation for the turbulence modeling as opposed to 2, 3, or even more. But anyway, the researchers here do something interesting. They are going to test 2 different mesh approaches. The first is where the y plus value is around 1, then when the y plus value is greater than 30. So you might be thinking, well, so what? What's the difference? Well, the reason why this is important is because when you have a y plus value of around 1, the K-Omega SST terminus model that they are using here won't use any Wolf functions in the boundary layer. What that means is that you won't be using general equations to assume what is happening in the flow very close to the wall, in the very lower region of the boundary layer. When the y plus value is above 30, then you'll be using these general equations, these Wolf functions. The difference being that you will likely get some different results, and the important point to note is, which is more accurate, is there a way where you don't need to use these general equations, these Wolf functions? Do you need to use them? Is it better? Is it not? Well, in table 4, we see the results of the two CFD approaches in the first 4 columns, and then the experimental results are in these last 2 columns here, CD and CL, CL and CD, sorry. So the title K-Omega SST high re WF means this is the K-Omega SST terminus model at high Reynolds number and using Wolf functions. The title K-Omega SST no WF means that the K-Omega SST terminus model was used, but no Wolf functions were used. So the very lower part of the boundary layer was calculated, and that's because the y plus value was 1 or around 1. So that means you need to use more cells too. So if you can use Wolf functions with fewer cells, it means it will be easier for you to simulate. Now anyway, something important to note is that the LEVCON tripped data is for an airfoil where the boundary layer was tripped. What that means is that the boundary layer was forced to become turbulent prematurely. That is done to approximate a higher Reynolds number, but it isn't exact. So validation data here is not 100% applicable here. It will be close, but there could be differences simply because of that tripping, which then creates a slightly different boundary layer to what would happen if you had a higher Reynolds number to begin with. But anyway, let's compare these two different CFD approaches with Wolf functions and without Wolf functions. So up until 15 degrees, both give very similar lift coefficients. From there, they start to diverge, and that makes a lot of sense because now we are approaching the stall angle attack. And so the boundary layer becomes more and more important. As such, these different boundary layer approaches with this Wolf function versus no Wolf function plays a larger role. And I should mention, actually, I think I've mentioned it, but before, if you want to see this paper, you can find it in the link below. But anyway, just moving on, it is clear that these differences do occur above about 15 degrees because probably this boundary layer is developing differently whether you have all functions or not all functions. So for example, at 18 degrees, the lift coefficient is about 1.5% different between these two approaches. As for the drag coefficient, the values start diverging from a lower angle attack at around 10 degrees, so this row here. And that is probably due to differences in the pressure drag because each version is predicting a different amount of separation and a different wake size because the boundary layer is a little bit different. So that tells us that there are some differences between using Wolf functions and not using Wolf functions, but they are small usually, at least in pre-stall angle attack. But how does that all compare to the validation data? Well, in figure 5, let's zoom in a little bit here. So here we go. So in figure 5, we see the validation data in the black dashed line. The green diamonds are the CFD with the Wolf functions, the red are without. The left plot is the lift coefficient, and we see that up until about 15 degrees, the CFD matches up pretty much perfectly. It's very impressive. Then above that, differences do creep in. This could be because of the artificial tripping of the boundary layer in the experimental data, or it could be because of the general inaccuracy of the terminus modeling, or it could be because of that mesh in the trailing edge section that isn't fanned out as much as what we were talking about before. Now the drag coefficients in this right figure here support this, I think, because you can see that the drag coefficient diverges from the validation data at least at a much lower angle attack. It works out at about 10 degrees. That kind of makes sense because the wake flow isn't resolved as well. So it might be that the mesh here is partly to do with this inaccuracy. Anyway, I think for pre-stall angle attack, the CFD fullest NACA 0012 is incredibly good, and you're not going to find too many better than this, and regardless of whether you have Wolf functions or not. So now let's move on to the CFD of the entire jet. So the authors say that when doing aircraft simulations, it's a good idea to have the entire domain's length at least 25 lengths of the car, that long. And the outlet should be at least 10 aircraft lengths downstream. As such, the inlet was 10 lengths upstream for their simulation, their domain, and the outlet was 20 outlets down, 20 chords downstream, 20 aircraft lengths. They call them chords, but I guess they're aircraft lengths too. So one really interesting thing is that they put the entire aircraft into this own rotation zone, this AMI region on this right here. You can see here. So they did this so that they can rotate the entire aircraft to different angles without having to remesh the entire domain. Now, I think they went with this approach because that reduced the number of overall cells in their domain. Because if you look at the left part of the figure 9, we see some gray shapes. Let's zoom in a little bit here. So these like gray little cut-ins here. The overall shape is the domain, so it is like shaped as like this half oval in the free stream direction, but then the circular section in this cross section. But we see that the actual aircraft was in the center here, and then behind it there is this refinement zone that extends back, this SD. That stands for slipstream domain. That's the refinement region. Now, if the aircraft were to remain level and angle of attack were changed through the inlet flow angle, that refinement zone wouldn't be in the wake that much. For the same reason as that 2D airfoil, where the wake would come down more, so you need to make this refinement zone fan out more. So instead of making that refinement region much larger, they opted to rotate the entire mesh of the aircraft. That was instead of making that wake more refined, at least from what I can tell. That apparently reduces the computational time because you don't need to remesh every time, but you still get a different angle of attack and the wake is refined. So it should give decent accuracy with fewer cells, I think. Also note that for some reason, they decided to make the fine meshes refinement region more of a cone that flares out downstream than just the constant width which you have for this coarse and medium mesh in this upper part of the figure. So it makes sense from that point of view for the fine mesh to be like that, and really all meshes should be like that if you think about it, because the wake will flare out too. So by having that refinement region flaring out, you capture that more and you get more accurate results too. So I imagine you should do that probably for the coarse and medium meshes too. Anyway, in figure 10, let's zoom out a little bit here and go to figure 10. We see the mesh with various refinements from the coarse and medium on the left to fine on the right. Now the Reynolds number was 92.5 million. So the authors decided to use a Y plus value of 50 to reduce the number of cells needed. They say that the mesh that they used here, they range between 42 million cells and 82 million cells. But if you wanted a Y plus of 1, you would need 500 million cells approximately. And they estimate that that would mean you need RAM in the terabytes. I'm not sure about that. I think you'd probably need more, about 500 million. But yeah, anyway, it's well far more than what most people have access to. Anyway, as a result, with their 42 to 82 million cell mesh, the simulation took around 100 hours to do each time on average. And they tested 90 different configurations. As a result, it took 7 months for them to run all the configurations on all the machines they had. They have their machines listed here, which have, I think, 6 computers ranging in number of cores/threads and memory. And they used all these, they flogged them for like 7 months to get all of these simulations done. So that's pretty insane. Anyway, in table 10, we see the angles of the jet that they tested. If I zoom out a little bit as well, here we go. So note that each of these angles were also tested with 3 different LEVCON deflection angles. So the leading edge extensions were deflected to 10 degrees, 20 degrees, and 30 degrees for each one of these aircraft angles too. So that's a lot of simulations. That's 45 simulations right there. And each one takes 100 hours. That's 4,500 hours just there of computational time. Plus everything else that you need to do as well, including meshing, post-processing, and just getting the simulation ready to go in terms of geometry, importation, etc. So anyway, they had to run a huge number of simulations, and no wonder it took over half a year. So I'm really impressed with their dedication. And the amount of storage that need to store all the data from the simulations would probably be like tens of terabytes too. Anyway, let's now jump to the mesh independent study, which is in tables 13 to 15. We get all the data here, but it's a bit hard to see. So let's go to figure 12, because all the data is plotted there and it's much easier to see what's really going on. So let's zoom in, and here we go. So the green diamonds are for the coarse mesh, the blue squares are for the medium mesh, and the red triangles are for the fine mesh. And for all 3 meshes, they give similar results across the board. For example, in figure 12a here on the left, the lift coefficients are bang on, as are the drag coefficients to the right here for all these meshes. And even the moment coefficients in figure 12D, they're bang on pretty much each other as well. There's a little bit of wiggle about, but the moment coefficient is very sensitive compared to the lift and drag coefficients. So to get them so close here is very impressive too. So really any mesh would have been fine here. Now, while the grid independent study was good, they don't have any validation data, which is understandable because it's hard to get validation data of the jet, and especially one that is just generally designed by them. So let's keep that in mind going forward, that there's no validation data for the CFD. So now in figure 13, we see the effects of the LEVCONs at different angles compared to the jets at different angles too. So figure 13A shows a lift coefficient versus the angle of attack. The green diamonds are again the LEVCON at 10 degrees, the blue squares are the LEVCONs at 20 degrees, and the red triangles are at 30 degrees. So it's clear that at a higher LEVCON angle, we don't necessarily produce the best lift coefficient, because while at lower angles of attack, there's not much of a difference between the lift coefficient. When you get to about 20 degrees, let's zoom in a bit here, 20 degrees and up to about 30 degrees, the LEVCON at 10 degrees gives a much better lift coefficient than the other two. And it isn't until 35 degrees that all produce similar lift coefficients again. So right there, that's good evidence that having movable LEXs, so these LEVCONs, is good in that you can tailor the angle to give the best lift coefficient depending on the jet's angle. Now in figure 13, we see again that the LEVCON angle does affect the drag coefficient, but this time it's less. It doesn't affect it as much as the lift coefficient. Interestingly, it affects the drag coefficient at the same angles as the lift coefficient, so around 20 to 30 degrees. But here, the greater the LEVCON angle is, the lower the drag coefficient becomes. So there's a trade-off here. Figure 13C shows the lift to drag ratio, and now things get really weird because for the lift and drag coefficients, we saw that around 20 to 30 degrees, that's where you significantly get a difference between these LEVCON angles. So in the lift to drag ratio, you might expect that these changes occur here too. But nope. Here it seems that the changes cancel out. So the lift to drag ratio at these angles of attack were unaffected by the LEVCON angle. But when you go to about 5 degrees, so this peak here, let's zoom in a bit more. It seems that the LEVCON at 30 degrees gave the highest lift to drag ratio. That is surprising considering that the lift and drag coefficient graphs don't really show much of a difference at this angle. But with the lift to drag ratio, any changes, minor changes or even major changes get amplified. So that's why we are seeing these changes here. But also note that these are about a 5% change. So maybe that is within the error of the CFD too. That could be the case. Now in figure 13, we see the moment coefficient here. And here we see that for each LEVCON angle, they produce a negative value. So that means that a nose down pitching moment is always produced with any of these LEVCON angles. And that means that the aircraft is longitudinally stable. However, as the LEVCON angle increases, so does the pitching moment coefficient. So deflecting the LEVCON more and more makes the plane less stable, which isn't such a bad thing here because this is a jet and it should be maneuverable. And the moment coefficient values we see here are very negative to begin with. So moving them more to the zero line may not be such a bad thing. It may make the aircraft more agile. So that's great news again, because that means that you can use the LEVCON angle to change the aircraft performance. But why? Why does this happen? So in figure 14, we see the streamlines over the jet when it's flying at 20 degrees. Let's come down here and zoom out a little bit. Okay, so we can see all of them now. That's good. So the top row is for the jet with just the regular fixed LEXs or LEXs. The next 3 rows are for 10 degrees, 20 degree, and 30 degree LEVCON angles. And the 3 plots in each row is just for the streamlines at different positions. And comparing all the LEVCON figures with the LERCs figures, it is clear that the LEVCONs do a much better job controlling the flow. The vortices coming off of them don't seem as big, so many of them, so they may be weaker, you can't tell though from this information presented, but they remain tighter, and they don't seem to break down as quickly as with the LERCs, as we can see once you get to the trailing edge of the wing, they've already fanned out a lot and they're in the process of breaking down. So that makes sense, because if you can deflect the edge of the LERCs more, and that's making the vortex, you can then pitch it so that the vortex is still forming and not breaking down. You can control that. That means that you should be able to fly to high angles of attack without stalling. And actually, if we go back to figure 13, we can kind of see that where the clean model, here we go, the solid dash line here, the thick black one, we can see that's just with the LERCs, and stall occurs a little sooner maybe, and it's a sharper stall pattern definitely. So the LEVCONs are softening the stall and even delaying it potentially slightly. Now in terms of how the different LEVCON deflection angles affect the streamlines, well, in figure 14, zoom out a little bit more, a greater angle comes with a seemingly bigger and stronger vortex. You can see as you go down the page, these vortices get stronger, they get bigger and possibly stronger. So looking at figure 15 and 16, which are the exact same type of plots, but for the jet at 25 to 31 degrees, the standout trend is that the LEVCONs seem to produce much more stable vortices compared to just the LERCs. The vortices seem to be tighter and they're more coherent as you head to the back of the jet. Whereas with the LERCs, you can see they're like breaking down already and becoming very spindly. And that also happens here too. That's at 31 degree for the aircraft as opposed to 25 degree. So it seems like the LEVCONs are definitely controlling the vortices much better and preserving them. So now in figure 17, we see the Mach numbers at various cut planes through the jet. And let's just quickly explain what these figures mean. So the top row is just for the LERCs, while the bottom three rows are for the LEVCON at 10, 20, and 30 degrees, respectively. The left column is the jet at 20 degrees, the middle is 25 degrees, and the right is 31 degrees. And if we look around the LEVCON, it seems like generally it's increasing the Mach number. The colors are greener and yellower, which means that they're closer to, this color bar here shows 0 is blue and 0.55 is red, or 0.56. So what that means is that potentially they are reducing the critical Mach number of the aircraft actually, because we are getting higher velocity flow over them than just the regular LEXs. So if you don't know what the critical Mach number is, then check out our video on YouTube called Aero Fundamentals number 31, Critical Mach Number. In a nutshell, the critical Mach number is the free stream Mach number at which sonic flow first appears over the object. That also means that a lower value results in not being able to fly as fast before getting a lot of drag due to wave drag. So what that means here is that perhaps the LEVCONs aren't great here because we are getting a higher velocity, which means that the critical Mach number is probably dropping, and that's going to result in more drag for the jet. But from the angle of controlling the vortex and even improving the jet's lift and drag at a very subsonic speed, they're really good. And with that, we come to the end of this podcast. And just as a reminder, this was all done in OpenFOAM. And if you want to do something like this or other simulations, then check out our OpenFOAM courses on our website. And if you like this podcast, hit the like and subscribe buttons. And we'll see you on. Peace, amigos.